Hello, good evening, one and all. Uh, we'll start the session in few minutes. I hope I am audible and you can see my screen. Can anyone please confirm that?
Audible, ma'am.
Okay, thank you. So, so let's start with our problem solving session today. So, as you all know, we are having this session every Saturday from 5 p.m. to 7 p.m. So I have introduced myself last week. I don't know. mm, so I can introduce myself once again. So I am Susan, PhD scholar from Electrical Engineering Department at IIT Madras. Uh, so so every week we'll be trying to solve a few sample questions, which is not the assignment questions, but which will help you eventually to solve the questions and maybe help in your exam preparation. So let's start our session today with the week two. So last week we had a discussion on week one content and a few problems based on that. So these were the contents covered in week one. So let's move on to week two. So, what is being discussed in week two is something which is highlighted in blue color. So, this is a brief of lecture 4 to 6 in the video lectures. So, from these topics, if you see from the finite difference method, you have come across solving Laplace equation basically to understand I mean, hands-on programming uh, to to visualize voltage and electric field inside a parallel plate capacitor. And also, you have come across solving wave equation, telegrapher's equations with the okay. So then the discussion goes on reflection coefficient, especially when the load is an open circuit or when it is a short circuit or when it is a matched load. And then we hadn't discussed voltage bounds diagram. So today we will have some small sample numericals based on um these kind of these topics. So let's move on. So I request all of you participants uh, to make our interactive session uh, very active. So we will go ahead by solving the numericals during the session. So I can help you when and where you are getting stuck. So we'll try to um calculate or do the problems. All of you try to do it by yourself and let us have a discussion on maybe on chat or you can turn on your mic and talk. So that way it becomes better. So I have a bad throat today, so probably I may have to excuse for a while. So I might stop my mic for a while if I am not finding it comfortable. But definitely we will run our session as to my best ability. So so let us start with the first question which you are seeing on the screen. So this question is on a transmission, a type of transmission line, basically two types of transmission line. As you can see, this one is a coaxial transmission line and this one is a two-wire transmission line. This is very familiar to all of you. So there are some parameters given to us. Let's read that. So figure 1 shows a lossless coaxial cable and a two-wire transmission line given mu r epsilon r. Okay, so we are given with the relative permeability and permittivity values and A and B. So let me try to make you understand what is A and B. So this A is the inner radius and B is the outer radius. And in case of two-wire transmission line, B is the gap between the transmission line and 2A is the diameter of that transmission line. So, there are some equations written adjacent to this. So in case of a two-wire transmission line, these equations are to find the inductance and capacitance, and this in case of a this in case of a coaxial cable and this in case of a two-wire transmission line. So now let's go on to the question. Characteristic resistance of the coaxial cable and two-wire transmission line. So this is the first question. So to answer this question, the very first understanding should be what is characteristic resistance? What is the formula for that? That is root of L by C. So we know what is L and C. So try to solve it and let's have a discussion. So please see the equation. Try to take the substitute the values and try to find the answer. Let's wait for 1 or 2 minutes and let's have the answers. Okay, please do try. So to start with, I hope all of you are trying. To start with, um, in case of coaxial cable, I hope these steps are clear to you. So how to replace mu? We need to replace it as mu naught into mu r, epsilon naught into epsilon r. I hope you know the values. So maybe for some of you might have forgotten. So let me write it down here. Mu naught is 4 pi into 10 power minus 7 and epsilon naught is 8.85 into 10 power minus 12. So now we know all the values. Can we get the answers? I hope you are trying. So ln b by a is 20 by 5, which is 4 by 2 pi into root of mu naught. Mu r is 1. Epsilon r is 2.76. Can we have the answers? Anybody? So we have an answer. Thank you, Akhila. I hope all of you have tried and you are all close to the answer probably. So yes, our answer is approximately you get the characteristic resistance as 50 ohm. Now, can we do the same for a two-wire transmission? Like, so RC will be root of L by C, taking these equations into account. So let us write it down. So again, B by A becomes 4, and mu is, so this is divided by pi, and epsilon naught epsilon r. So can we have the answers? Sorry, there is B by 2A, so I made a mistake here. So it is not 4. So B by 2A becomes 2. So can we have an answer for this? Uh, so there is some answer. I think you need to recalculate. Uh, that's not the right answer. Can you try once again the calculation? So if there are any confusions in, please do ask. again, it's a wrong answer. It is coming close to 95 is a wrong answer. So maybe please do check this equation. It is b by 2a. It's not b by a as I wrote initially. So I think it's taking time. I'll just give an answer. Maybe all of you can check. So this simplifies to be 298.7 approximately. So very close to 300 ohms. So that is uh, characteristic resistance of a two-wire transmission line. So the next question is very interesting. That is, if a transmission line with characteristic resistance of 500 ohm is required, which transmission line would you prefer? So if you look at the characteristic impedance of coaxial cable, it was close to 50 ohm, and in this case, in two-wire transmission line, it was close to 300 ohms. So you can understand a higher characteristic resistance is if you are preferring, if you are going for a characteristic resistance of 500 ohm, the dimensions required in case of a coaxial cable would be very large. Say the A and B might be very large, might go very large. That is your inner diameter and outer diameter. If it goes on to a larger values, it is not preferable. So a two-wire transmission line is preferred. So the answer for this question would be our preference is two-wire transmission line if the characteristic resistance is very high of the order of hundreds of ohms, like 500 ohm or so. Okay, I hope this question is clear. Can we move to the next question? If there are any doubts, please do ask, or we'll move to the next question. I think I can move to the next question, taking silence as that you understood the things. Uh, okay, so next question is on voltage bounce diagram. So this was one of the topics discussed in the week 2 content. So I hope all of you might have already come across this. So let's have take a look at this transmission line setup. As you can see here, there is a 100-volt source, and there is a source resistance of 40 ohm, and at time t equal to 0 the switch is being closed, and this is our characteristic resistance of this particular transmission line. And to this line there is a load which is connected, which is 40 ohm. Okay, now at this is at position z equal to 0, and this is at position z is equal to l, meaning which l is the length of the transmission line, and the wave is propagating from z equal to 0 to z equal to l. Okay, now let's have a look at the question. What is being asked? Voltage across the load resistance RL undergoes a change at time instance. Okay, we need to know at what time instant voltage across RL will have a change. So that is our question. So to answer this question, we need to before going to this question in particular, let's have a look at how do we do the voltage bounce diagram of this. So, given a source voltage of 100 volt and a source resistance of 40 ohm and a characteristic resistance of 60 ohm, can we just calculate the voltage at Z equal to 0? Okay, so let us start with that step. So voltage at Z equal to 0 will be 100 into 60 by 60 plus 40. So this is purely the voltage division rule. So through which you will get an answer as 60 volt. So at Z equal to 0 you have 60 volt. Okay. Now this 60 volt will be transmitted. Okay. Now the other thing is, let's have a look at the reflection coefficient, especially if you want to write source reflection coefficient. Gamma S will be Rs minus Rc by Rs plus Rc. So what is Rs here? 40 minus 60 is the Rc, 40 plus 60. So this gives an answer minus 20 by 100, or I can say minus 1 by 5. Okay. Similarly, what is gamma L? That means reflection coefficient at the load end, which is nothing but RL minus RC by RL plus RC. So RL is 40 minus 60, again same 40 plus 60. So again you get the same answer, minus 0.1 by 5 or minus 0.2. Okay, so now we know the source reflection coefficient and the load reflection coefficient, and we also know what is the voltage at the Z equal to 0. Now let's have a drawing of the voltage bounce diagram. Say this is Z equal to 0 and this is Z equal to L. Okay, and so say this is the source end, so I will write gamma S is equal to minus 0.2, and this is the load end, so I can write gamma L is equal to minus 0.2. Now from time t equal to 0, okay, and from this z equal to 0 to z equal to L, within one transit time, propagation from z equal to 0 to z equal to L happens within one transit time. Okay, so we take this transit time, this is tau. Okay, the next is coming back 2 tau. Okay, again after reflection from here it goes back, this is 3 tau. Again at the load end there is a reflection going back 4 tau. Again going back 5 tau. So now you observe this, at the load end, when is the voltage going to change? At tau, 3 tau, 5 tau, 7 tau, etc. Okay, so this is the answer to our first question. Voltage across the load resistance, that means voltage at the load end, changes at time instance of, what is the time instant? It should be tau, 3 tau, 5 tau. That is an odd multiple of tau. So tau, what is the tau value here? What is the tau value here? Which is given here, right here, that is 0.5 microsecond. So when you say odd multiples, which among these becomes the choice? Can you please tell?
Option 3, ma'am.
Option,
3.
I think I couldn't hear properly. Option
Option 3.
3. Okay, option 3. So yes, option 3 is 0.5, 1.5, 2.5, 3.5. Yes, right. So this is The answer, right answer, that is tau at the time instance t tau, 3 tau, 5 tau, 7 tau, the etc. The voltage across the load resistance RL changes. If there is any doubts with this, please do ask. If there is no doubt, we'll go ahead to the next part of the same question. Okay, let's move to the second part. So the second part is at time t is equal to 12 tau, voltage on the transmission line at a point z equal to L by 2. So where is z equal to L by 2? It's exactly at the middle. So z equal to L by 2. Now we need to find at time 12 tau. Okay. So it goes on 5 tau, 6 tau, 7 tau, it goes on up to 12 tau. And at z equal to L by 2, that means at the middle of the transmission line, it is indicating the middle of the transmission line. What is the uh, voltage? Okay, so that is our question. So to answer that question, I think I need to help you with a better diagram. Okay, let me draw a better diagram. Same as we seen before. I'll just redraw it quickly. So this is z equal to 0 and this is z equal to L, and this is exactly at the center z equal to L by 2. And this is gamma s is equal to minus zero point 0.2 and gamma L is equal to minus zero point 0.2. And here we have 60 volt here, which is going to come here at tau and again reflect back, come here at 2 tau, then again go back here at 3 tau, 4 tau, 5 tau, 6 tau, and so on. Okay. Now let's have a look at the effect of this reflection coefficient. So when the first reflection happens at the load end, this voltage becomes 60 into minus zero point 0.2, and the next reflection happens at the source end. So again 60 into minus zero point 0.2 the whole square. Okay. Again the reflection happens here. So 60 into minus zero point 0.2 the whole cube and so on. Okay. Now the question is at a time 12 tau. Okay. What is the voltage at the middle of the transmission line? So let us write this voltages. Say first voltage is 60. What will be the second? What is this? 60 into minus zero point 0.2. Then third one is 60 into minus 2 the whole cube, and so on. And when it comes to the 12 tau, so you see when it comes to 4 tau, it is minus 2 raised to 3. So when it comes to 12 tau, it will be 60 into minus zero point 0.2 the whole raised to 11. Okay. So this is, so let me write it in a better way. So this is a GP for which the value of R is minus zero point 0.2. Okay. So the sum of a finite GP is 1 minus R raised to N. So minus zero point 0.2 raised to 11 divided by 1 minus R. So minus zero point 0.2. I hope this is clear and you can find the final answer. Any doubts in this calculation of voltage at time t is equal to 12 tau at the center of the transmission?
Ma'am,
Yes,
ma'am,
please.
Why 60 into minus 0.2 whole square not came, ma'am? Whole square 0.2 whole square.
Okay, so you see that the reflection coefficient at load end is minus zero point 0.2 and also at source end is minus zero point 0.2. So when it goes from the z equal to 0 to tau, it is 60. Once it is reflected, it became 60 into minus zero point 0.2. Again, there is a reflection here. So the second reflection coefficient is being just multiplied. So 60 into minus zero point 0.2 the whole square. Is that
Okay, ma'am. Okay, ma'am.
okay? So if you do the calculation, ah,
Excuse me, ma'am.
yeah, please.
Ma'am, for 100 tau, how do we calculate, ma'am? From assignment to the time second is 100 tau, but the
Okay.
reflection coefficient tau L and tau Z are totally differ. But here tau L and tau S is same, so we have to use the GP formula. But in
Hmm.
the assignment question, tau L and tau S are totally differ, ma'am.
Hmm.
But time period T equal to 100 microsecond. How to calculate it, ma'am?
Okay. So you are saying that the reflection coefficient at load end and source end was different.
Yes, ma'am. But
Okay.
at the same time, at the question, the RC, RL, the values are not given, ma'am.
Mm, I think I need to have a look at the question. Uh, okay, I think it will take time for me to load the question and find it out. Let's do one thing. The solution of this assignment will be uploaded. So let's learn the procedure, and if you still did not understand from the solutions which are uploaded, I'll discuss that question again in the next week because I haven't got the question right away. Uh, I can't discuss it immediately, but I will definitely note it down and I'll take it up in the next week. So the question is on bounce diagram, right?
Yes, ma'am.
Yeah, I'll take care of that in the next week. I need the question. Huh? Okay.
Okay, ma'am. Thank you, ma'am. Excuse me, ma'am.
Mhm. Yeah,
Ma'am, I
please.
missed the previous Saturday session, ma'am. How
Oh.
to access the session, ma'am?
So you have a, so there is in your NPTEL site you have a, link which will lead you to the PPTs and also the YouTube link. So I have uploaded the video in the YouTube channel. So you can get the link from that same Excel sheet. So that link is uploaded in the NPTEL site. It is not directly the YouTube link, it is a link to an Excel sheet. So that Excel sheet itself will have a link to the PPT which I am using and also the YouTube, I mean the video recording in the YouTube channel.
Okay, ma'am. Thank you, ma'am.
I think there is a message. For okay, Akila, I think she's trying to give some clue for the question asked. For 100 time constant, uh, transmission line will be short circuited and we need to apply KVL and KCL. Okay, so probably Abhinaya, you can look into this uh, because I am not having the question right away. I can't comment on this presently, but we'll take it up in the next week definitely. Okay.
Okay, ma'am.
So this answer for this would be approximately 50 volt if you solve, and I hope this is fine. Hmm. So let's move to the next question. Okay. So the next question is, at time t is equal to 12 tau, current flowing through the load resistance. So this is very easy. Now you know the voltage across the load resistance. I hope you remember. So this is the voltage across the load resistor. Can we find the current? It's a very simple. All of you can try. Even if you don't know the bounce diagram also, you can try this. Please give me an answer for the current. Voltage across is 50. And what is the load resistance value? That is, I think, 40. So what will be the current? Quickly, please. Current flowing through the load. We know the voltage across the load. We know the resistance. Just a division.
1.25 ampere, ma'am.
Yeah. 1.25. So this is our current. Okay. So let's move to the next question. Okay. So we have discussed this one and this one. Let's move to the next. Okay. If the source resistance Rs is 0, okay, voltage across RL at a time instant 10 tau. Okay. So this is a special condition. When Rs is 0, what will be gamma S? Simple question. Please do respond. When Rs is 0, what will be gamma S? Very simple. Before, yeah, yes, Akhila, you are right. Gamma S is minus 1. Okay. Now, gamma L, there is no change. So, let me write it. Gamma L is minus zero point 0.2. There is no change. And, okay. Now, let's have a redraw of the voltage bounce diagram. So, all of you can help me with that. So, now when you have a redraw, this is Z equal to 0 and this is Z equal to L. This gamma L is minus zero point 0.2 and gamma S is minus 1. Can you tell me what will be the voltage at Z equal to 0? Is it 60 volt? So now this Rs is not present. Yes, you are right. So now Rs is right. Rs is not present. The voltage will be 100 volt. There is no voltage division, so it is directly 100. Now, after reflection, so at tau there is a reflection from the load end. After reflection, this becomes 100 into minus zero point 0.2. Okay. Again, here at tau, 2 tau reflecting from the source end, this becomes minus 100 into minus zero point 0.2. Okay. And go reach here at 3 tau. Again, there is a reflection. So, after reflection, minus 100 into minus zero point 0.2 the whole square. And this goes on. And this goes on till, so okay. Now we need to understand what is the question asked. The question is at 10 tau. Time t is equal to 10 tau. So at time t equal to 10 tau, you do the calculation. Okay. And also remember, this is being asked at the load end. Okay. Now the GP becomes slightly different. There is nothing much change. There is a plus minus plus minus. So you can do that adjustment. Okay. So I hope you can try this out by your own. You once you try, you must get an answer approximately 100.032. Okay. Please do try. Now, next question. This is a different view. You see, at time t is equal to 1.26 microseconds. So here it is. So see that our time tau is zero point 0.5 microsecond. Okay. So 2 tau is 1 and 3 tau is 1.5. Okay. So 2 tau is 1 microsecond, and at the middle of the transmission line, if you imagine, z is equal to L by 2 time tau by 2, that means 0.25. Okay, so 2 tau plus tau by 2, that means it is 1.25 microseconds. So immediately after the middle of the transmission line. Okay, uh, and at time t is equal to 1.26 microseconds. Okay, so that will be somewhere here. Okay, so the question is, at z equal to 0, at z equal to L by 4, at z equal to L by 2 and 3L by 4, at each locations on the transmission line, can you tell what will be the voltage? So if you know what will be the voltage, you will be able to answer the question. So the question is voltage at the following points. That means it is different locations on the transmission line. Where is that voltage greater than 48 volt? That is the question. So to answer that question, what we need is, we need to understand what is the voltage at these different locations. That's all. So to have an understanding of that, let's have a look at this. So I think okay, this question has to be answered with 16, keeping in mind it is 60, because our fundamental question was 60. Okay, so this was this 100 came because of a special case. So let us make it 60. Uh, so let's have a change. Gamma s is minus 0.2. So this is a part of the question. So that's why I'm making these changes. This is a part of the first question only. So let us make it 60. 60 into minus 0.2, 16, sorry, 60 into minus 0.2 whole square, 60 into minus 0.2 whole cube. Okay. Now, 60 into minus 0.2, what will be the value? It will be minus 12. And 60, and that into minus 0.2 will be 2.4 volt. Okay. Now let's see the transmission line part. Say at z equal to 0, z equal to L, z equal to L by 2. Okay. So 60. So this is 60. This is minus 12. And this will be 2.4. Now let's have a look at what happens between z equal to 0 to z equal to L by 2 and immediately after this. Okay, let's divide this transmission line into two parts. So z equal to 0 to L by 2, you see 60 minus 12. So what will be the total voltage? There will be 60 minus 12 and plus 2.4. Okay, so first reflection, second reflection, first reflection, second reflection, and this is the time, that is t equal to 1.26 microsecond. Okay, so from z equal to 0 Z equal to L by 4, Z equal to L by 2. That means till the middle of the transmission line, you need to add all these voltages. So what you will get? 60 minus 12, 48 plus 2.4. The total voltage will be 50.4. And you see, immediately after the transmission line, that is, it's middle of the transmission line, that is at the time t is equal to 1.26 microseconds. So this has transmitted up to here, but after that, that means at z equal to 3L by 4. So this is somewhere here, 3L by 4. This is after a time 1.26 microsecond, and at z equal to L. Okay, so these two we have only 60 and minus 12. So what will be the total voltage? 60 minus 12, which is equal to 48 volt. I hope this is clear. If there is any doubt, please do ask. I can explain it once again. So this, you need to understand the position of the transmission line and also the time.
Ma'am, please kindly repeat again, ma'am.
Okay. I'll do that in a, okay. So let's have a look at the bounce diagram once again. This is z equal to 0, z equal to L. This is z equal to L by 2. And gamma L is minus 0.2. Gamma S is again minus 0.2. So this is 60. Okay. And this is at time tau. And this is at 2 tau. And this will be at 3 tau. Okay. Here tau is 0.5 microsecond. 2 tau is 1 microsecond. And 3 tau is 1.5 microsecond. Okay. Now we haven't reached this. Okay. So we are stopping somewhere here. Okay. So somewhere at the middle of the transmission line. Okay. Now this is 60. After first reflection, 60 into minus 0.2, this becomes what? Minus 12. Now coming back, reaching here, there is another reflection. So minus 12 into minus 0.2, that is 2.4. Okay. Now this reflection has happened and this has propagated. Okay. And this has propagated till the middle of the transmission line, which happens at what time? So this is 1 microsecond and this is 1.5 microsecond and this is 1.25 microsecond. Okay. So till, so the transmission we are telling at some 1.26 microseconds. Okay, we are talking about a time at 1.26 microsecond. Okay, so then the transmission happened till here, somewhere immediately after the transmission, middle of the transmission line we are discussing. So from z equal to 0 to L by 2, what is the total value? 60 minus 12 plus 2.4, which is nothing but equal to 50.4. But if you see a time after L by 2, that means 3L by 4 and at L. Now what is happening? It is not propagated till here. The 2.4 has not propagated. So what will be the total voltage? Only 60 minus 12, which is equal to 48 volt. I hope this is clear now. Can I have a response?
Yes, ma'am. Yes, ma'am.
Okay, okay. Thank you. So I think it's clear to everyone. So the question was, where is the voltage greater than 48 volt. Okay, so voltage is greater than 48 volt at Z equal to 0, at Z equal to L by 4, which is 1/4 of this. So, and also at Z equal to L by 2, because all these points the voltage is 50.4, but immediately after the center of the transmission line it is just 48 volt. Okay, so this was a question on voltage bounce diagram. So I hope you got the understanding of voltage bounce diagram. Now we'll move on to another question, which is rather very simple. So all of you can try this question. Uh, so this is the length of the transmission line, a 40-meter lossless transmission line of characteristic impedance. So Z0 is given to us as 50, or I can write it as RC. Okay, and the velocity is 2 into 10 power 8 meter per second. It is connected to this source. Okay, now the question is, what is C, what is L? Okay, so you are given with RC and V. So this kind of a question had been discussed in the last week. RC is what? Root of L by C. What is V? 1 by root of LC. So with the knowledge of these two, can you find C and L? All of you please do try. I have done a similar question last week also. Meanwhile, I'll take a short break. I'll be here. Please do try, and please do give your answers in the chat. So I hope you could try something. So the clue is RC into V. If you take RC into V, what do you get? Root of L by C into 1 by root LC. Yeah, I think there are a few answers already. I hope
Ma'am, L equal to 0.25 microhenry, ma'am.
L value. Yes, yes. Yes, I think I need not explain this. I think all of you understand 0.25 microhenry per meter. And C, someone has given the answer 100. Can you please tell the unit as well? Akhila.
0.1 nanofarad, ma'am.
Yeah, so if you say in picofarad, it's 100 picofarad per meter. Okay, and could you try this gamma L and gamma S? If at all anybody is just stuck with this, this is the clue. RC into V will give you 1 by C, and RC by V will give you L. I think it's familiar, the equation for gamma L and gamma S. RL minus RC by RL plus RC. And I hope you have noticed this short circuit thing. Yeah, yeah. Yes, Gokul and Akila, you are right. So gamma L is -1 and gamma S is 1 by 3. Okay, so let's move on quickly to the next question. I hope this was a very simple question. Okay, okay. So the next question is the parameters of a certain transmission line operating at 600 mega radian per second. So this is basically the omega, 600 into 10 power 6, and LCRG. So I hope you all know R, L, G, C are the primary constants of the transmission line. So all these values are given to us, and the indication that R and G are present. Is it a lossless transmission line or is it a lossy transmission line?
Lossy.
Yeah, it's a lossy transmission line, right? You are right. So, how do we calculate the attenuation and the phase constant? So, all of us know the propagation constant is gamma is equal to root of z into y. Okay, what is z? R plus j omega l, and what is y? It is g plus j omega c. Okay, so once you know that, you can calculate gamma, and gamma is actually alpha plus j beta in its rectangular form, where alpha represents the attenuation constant and beta represents the phase constant. Okay, and to to look at the second part of this question, the characteristic impedance Z0 is root of Z by Y. Okay, so once you get the answer for that, so that if that is in complex, so it's a complex impedance. If it is real, it's a real impedance. That's all. A real, I mean, it's a characteristic resistance. So if it is particularly a complex impedance, we call it as a characteristic impedance. Okay, how to find if the medium is lossy? So there is a question from Gokul. So very simple. See whether R and G is present or not. So resistance and conductance. Uh, so these two, R and G. If R and G both are 0, then we say that it is a lossless transmission line. Otherwise, it is a lossy transmission line. Okay. So that's a simple answer to that. So here, because R and G are present, we say it is a lossy. Okay, let's try to. I think all of you have a calculator which you can, maybe you can try with the online calculator also. If you have a rectangular form, you can definitely convert it to polar and then do these square root of calculation. So let's start with this z first. So r plus j omega l. So 20 plus j into, so omega is 600 into 10 power 6 and l is zero point 0.4 microhenry. So 10 power minus 6. Okay. So this will turn out to be 20 plus j 600 into 0.4 will be 240. So 20 plus J 240. Can we convert this to polar? That is 20 plus J 240 converted to polar form. Similarly, do it with Y, that is G plus J omega C. So 80 millisiemens. So please note 80 into 10 power minus 3 plus J into omega will be 600 into 10 power 6 into C will be 40 into 10 power minus 12. Okay. 0.08 plus J into 0.024. So this Z and Y converted to from rectangular to polar. So once you convert it to polar, gamma is equal to root of Z into Y. So you need to multiply the polar numbers and take a square root of that. So when you do a multiplication, multiply the magnitudes, add the phase values, and when you take a square root, you take a divide by 2 in the magnitude, sorry, square root in the magnitude, and divide by 2 in the phase. So can anyone please tell what is the polar value of Z? So some answer is coming 2.8 plus 3.47. So Akila, I believe that is gamma, reflection coefficient. 2.8 plus 3 what is that? 3.47 J. Okay, so she's giving the final answer of gamma. So I hope this is clear. So if somebody is having a doubt, I can just quickly write. So this is 240 angle 85, and this Y will be 0.08 angle 16.7. So how do you take root of Z into Y? Multiply 240 and 0.08, take a square root. Okay, 240 into 0.08 and take a square root. Now add 85 and 16.7. So what do you do with the angle? 85 plus 16.7 divided by 2, because it is under square root. So that will be your gamma. So once you have this in polar form, convert it to rectangular and you will get this answer. Is there any doubt? I hope everybody knows this. I know I need not spend time much. So similarly, in case of characteristic impedance, can you give me an answer? This will be like 240 angle 85 divided by 0.08 angle 16.7. So divide the magnitudes, take the square root, subtract the angles, divided by 2. What you get will be a polar form converted to rectangular form. Can we have an answer for Z naught? there is some answer. 45.37 plus 30.6. Yeah, right. You are right. That's the right answer. So that is the characteristic impedance. I hope all of you are getting this. Probably you will be close to this. All of you can try. Now the next question is on that is a slightly you need to understand. So if a voltage wave travels 20 meter down the line, so 20 meter it is going to travel. Amplitude is reduced by so and so percent and phase is shifted by so and so degrees. So this is the question. So if you remember, you calculated alpha and beta in the first part of this question. So what was alpha? Alpha value, I can just write it down here. Alpha was 2.76 Napier per meter and beta was 3.41 radian per meter. So we know per meter what is the attenuation constant and per meter what is the phase shift. I can say phase constant is nothing but the phase shift. So for 20 meters, do calculate this. So how do we calculate? Simply multiply. So the phase shift for 20 meter will be 3.41 into 20. So remember this 3.41 is in radian. Okay. So whatever answer you get will be 68.2 radian. So once you know the radian, you need the answers to be in degrees. What do? Multiply it by 180 by pi. Okay. So your final answer will be 3.907 into 10 power 3 degrees. Okay. Similarly, look at the attenuation constant. So what is this attenuation constant giving you? It is giving you how much the reflection, how much the amplitude of the wave will get reduced. Okay. So how much the amplitude will get reduced? It is e raised to minus alpha z. So if it is e raised to minus alpha z, where z, or I can say L, length of the transmission line. So e raised to minus 2.76 into L is 20 meter. So it will be e raised to minus 55.2. So if you calculate this, you will get 1.064 into 10 power minus 24. So this much will be the attenuation. Okay, this is the attenuation constant and this much will be the attenuation. So how much will be the amplitude reduced by? Okay, when you say reduced by, we have to take it like 1.064 minus 1 first thing. So that will be 0.064. To make it in percentage, so multiply it by 100. So you will get it as 6.4%. Okay. Now there is a multiplication factor. Don't forget, that is 10 power minus 24, which is here. So the answer will be 6.4 into 10 power minus 24%. I hope this is clear. If there are any doubts, please do ask. Okay, I think we can move on. Okay, so this is uh, so this question you have to. Okay, this is a question wherein you have to say. So out of these five options, uh, what is the implication of this statement? Okay, so there is a statement. What is that statement? Characteristic impedance of a transmission line being purely real. Okay, what does it imply? So does it imply A, B, C, D, E? So that is the question. So we need to go through each of the statement and see whether it implies the same. Okay. So first thing, characteristic impedance. What is characteristic impedance? Z naught. That is root of R plus j omega L divided by G plus j omega C. Okay. When this will become purely real? One condition, can you tell me any of the condition when this becomes purely real?
When R and G are 0.
Yes, right. That is right answer. When R and G are 0. Okay. That is R equal to G equal to 0. Z not become root of L by C, which is purely real. Okay. Now, is there any other chances for this Z naught to be purely real? That is the question. That is the uh, understanding which you should have.
When the frequency is very less compared to the resistance and conductance.
Okay. Mm,
That is
okay.
omega L is less than R.
Ha ha. Okay. Okay. Now, okay. Somebody has answered option B. So let's see what is option B. So according to Akila, when it is a distortionless line, that is when R by L is equal to G by C. Okay. So let's say what happens when it is a distortionless line. Z naught is equal to what? Root of R plus J omega L divided by G plus J omega C. So let's take out L, R by L plus J omega, and C, if we take out G by C plus J omega. Okay. Okay. Now, this could be approximated to root of L by C when R by L is equal to, sorry, okay, when R by L is equal to G by C, okay, so R by L is equal to G by C, so I can write it like R by L, okay. So this and this will get cancelled and your answer becomes root of, it's not approximation, it's root of L by C, okay. So when it is a distortionless line, that is when the ratio R by L is equal to G by C, in that condition also your input impedance is purely real, okay. Sorry, the characteristic impedance is purely real. So the first statement, it could be a lossy or lossless line, okay. It could be a lossy or lossless line. So distortionless line is a lossy line where R and G are present, okay. But only thing is the ratio R by L is equal to G by C. So the impedance, characteristic impedance can be real in case of lossy and lossless line. Okay. In lossless line, this is the condition, so you get purely real. In lossy line, whenever it is a distortionless line, we will have this to be purely real. Okay. So right away I can tick these two options A and D. So this statement's implication. Okay. Now let's go to B and C. Okay, B and C is on phase constant. Okay, well, you know phase constant is beta. Okay, so how do we know gamma is alpha plus j beta? I can write gamma as root of z into y. So let's have a simplification, root of r plus j omega l into g plus j omega c. Okay, so what is this? Root of r plus j omega l, let it be like that, and let me replace this g. So from distortionless lines condition, what is g? Rc by l. Okay, so Rc by l, I will replace g with the Rc by l plus j omega c. Now square root of r plus j omega l into, let's take c outside, and what do you get? R plus j omega l. If you cross multiply and divide it by l. Okay, so what do you get? Root of c by l into r plus j omega l. So this is what? Gamma. Okay, what is alpha in this? R into, so what is the real part? Real part is r into root of c by l. What is the imaginary part? That will be beta. So beta will be omega, root of c by l, root of c by l into omega l, or I can write it as omega into root lc. Now you see beta is proportional to omega. Okay, phase constant is proportional to frequency, the angular frequency. Okay, now the statement out of B and C, which statement is correct? Is phase constant a linear function or a quadratic function of frequency?
Linear function.
Yes. So it is C. Option C is right, but option B is wrong. Now let's evaluate the last option. How about phase velocity? Is it a function of frequency?
No, it is 1 by root LC, so it's not a
Yes.
function of frequency.
Yes, exactly. So omega by beta, omega by, what is beta here? Omega root LC. So we know that Vp is 1 by root LC, which is not a function of frequency. So this is also a wrong implication. I hope this question is clear. Any doubts? Okay, if there are no doubts, we'll move on to the next. Okay, so so let's read out this question. 60 ohm lossless transmission line. So Z0 is 60 ohm, operated at 60 megahertz. So F is 60 into 10 power 6. Velocity on the line V is 3 into 10 power 8 meter per second. And the line is short circuited at the load end. When you say line is short circuited at the load end, that means RL is 0. Okay. In that case, what is the input impedance? And this is for a lossless transmission line. Can anyone please give me an equation in this condition? For a short circuited transmission line, I mean short circuited at the load end, which is a lossless transmission line, what is the input impedance equation? I think I can give you the equation. Probably you might have gone through. Yeah. I think if you are giving the answers, right. J Z0 tan beta L. Okay. So this is the simple equation which you need to uh, just understand to answer this question. Say if it is an open circuited at the load end, could you say in case of an open circuited what will be Z in?
Minus J Z naught cot beta L.
Yes, right. So that is something which you need to just remember. So this is for a lossless transmission line. If it is a short circuit and if it is an open circuit. Okay. So let's answer the question here. Input impedance which is being asked at Z equal to 1 meter from the load. Okay. So J into what is Z naught? 60 tan of what is beta? How do we find beta here? Omega by Vp. Omega is 2 pi into 60 into 10 power 6. And what is Vp? 3 into 10 power 8. Okay. So you get it as 4 pi by 10. So for beta is 4 pi by 10. Beta into L is 1. So that will be Zn. Can we have an answer? Okay. 184.66J. Okay, fine. Now how about at Z equal to 2.5 meters? So nothing, just substitute this with 2.5. What is Z in? Yes, that is 0. I hope this was an easy question. Can we move to the next? Okay. Uh, Again, this is a simple question. All of you can try. Please do try. From the very basic equations, you can get the answers. Please try. Please type your answers in the chat. All of you, please try. You know that the characteristic resistance equation is root of L by C in case of a lossless transmission line. You are given with RC, you are given with L, you have to just find C. units please. 96.4 supposed to be, yes, picofarad. It's already here. Yeah, 96.4 picofarad per meter. Can we have the next Vp? Answer for Vp. Vp is 1 by root LC. I expect answers from everyone. All of you can give the answers. So the phase velocity answer is yes, 1.44 into 10 power 8 meter per second. Now beta. Yes, beta is omega by Vp. Omega is basically 2 pi f. So 2 pi into 80 into 10 power 6 by Vp is 1.44 into 10 power 8. So it will be 3.48 radian per meter. Now reflection coefficient. We know the load resistance. Find out the reflection coefficient. RL minus RC by RL plus RC. So 60 minus 72 by 60 plus 72. I think there is an answer. Yes, minus 0.1. I hope this was a very simple question. It was just to give you a feel of solving the sample question. Okay, now let's look at this question. It's a lossless transmission line with Z0 equal to 50 and gamma is also given. So gamma is 0 plus j.2 pi. If you notice, alpha is 0. What is the implication of alpha is 0? Anyone?
Lossless medium.
Yes, it's a lossless. So there is no attenuation. So gamma is just j.2 pi. Okay. So we can straight away write beta is 0.2 pi. Okay. And now ZL is also known to us. The question is L and C. So this is again a simple uh, understanding. L will be Z0 by V. So Z0 is 50 by, what is V here? So V we need to calculate, or Vp or V we need to calculate. Vp will be omega by beta. Okay, 2 pi into 60 into 10 power 6 divided by beta is 0.2 pi. So what is Vp here? Six into 10 power 8 meter per second. So once you know the Vp, you can substitute here and tell the answer for L. Can we have the answers for L and C also? How do we find C? 1 by Z0 into V. 1 by 50 into 6 into 10 power 8. Okay. So your L is 83.33 nanohenry per meter. And how about C? Capacitance is 33.33 picofarad per meter if you calculate. Okay. Now the last part of this question, shortest distance from the load at which Zin is purely resisting. Can we have any clues on this, how to solve this part? So we know the expression for input impedance. For that input impedance to be purely real, what is the distance? Shortest distance from the load. So let's write down the expression first in case of for the input impedance. Z0 into ZL plus JZ0 tan beta L. So let us write it by capital L divided by Z0 plus JZL tan beta L. Okay, this is the expression for input impedance in case of a lossless transmission line. So what is Z0 here? Z0 is 50. Z0 is 50. What is ZL here? ZL is 60 plus J80 if you look at the question. And what is beta here? Beta is 0.2 pi. Okay. Now you know all these. Substitute in this Zin expression. So Zin is equal to 50 into 60 plus J80 plus J50 tan of beta L. So beta we already know 0.2 pi into L divided by 50 plus J, ZL is 60 plus J80 into tan 0.2 pi L. So this is the expression for Zin. Now what is our understanding? So this Zin has to be purely real. That is our question. If this Zin has to be purely resistive, okay, that means it should be purely real, resistive or real. What is the shortest distance from the load? Okay, so we are being asked what is at what L Zin becomes real or purely resistive. So how do we do that? take the imaginary part of this expression. Okay, take the imaginary part of this z in. Okay, equate it to what? 0. Once you equate that to 0, you will get L. Okay, so that is the clue to this question. Can you all try this out and find out what is L? So to simplify this, we have to expand this expression for Z in and then find out L. I hope all of you can try this and give me an answer for L. Mm, there is some question, I think. Sorry, I was just logged out. Okay, is there any question? So once you, okay, there is an answer for L. I think that is wrong. You need to do a recalculation. So I can write a few steps for help. So please do calculate by yourself. So once you simplify this expression for z in, so basically what you need to do is take the imaginary part of z in, equate it to 0. Okay, when you do that, it is minus 3600 plus 4000 minus 6400 tan of 0.2 pi L plus 2500 tan 0.2 pi L, which is equal to 0. Okay, once you do that, you get tan 0.2 pi L is equal to 0.1025. From that, L is 0.1625 meters. Please try this out. After simplifying it, you must be getting this answer. Final answer for the length is 16.25 centimeters. It's a bit of calculations are required. You need patience to do the simplification, but you can definitely get the answer. Now we have some time left. If there are any questions, you can raise.
Ma'am, where you are uploading the videos, ma'am?
Uh, just a moment. I can just share my screen and
Yes, ma'am.
okay. So this is the YouTube link of the recording. And this is the link, Excel sheet link, which will be updated every week. Is there any other questions?
No, ma'am.
Okay, so probably you'll find this link also in the NPTEL site. I'm just having a look. It must be there. So I think the NPTEL team is yet to upload those links. But you can definitely look at this chat message, wherein I have shared a link of the Excel sheet in which there will be a weekly update of the YouTube link and also the PPTs. So other than me, there is one more TA who will be handling the session on Tuesdays, I think. So mine will be Saturday 5 p.m. to 7 p.m. every week. And if you just go to the YouTube link, maybe you can subscribe and you can get the update of the next video. I think that's so. If that is all we have today, then we can wind up the session. Thank you all for joining.
Thank you, ma'am.
Thank you.